Have you ever looked up at the night sky and wondered how big our galaxy really is if you live far from city lights and the sky is clear enough? You might have seen a faint glowing river stretching across the darkness. That hazy band is our home, the Milky Way, a cosmic city so enormous that every place humanity has ever explored, every mountain, every ocean, every civilization, and every person who has ever lived occupies only a microscopic corner of it. Most people know the Milky Way is large. What few truly grasp is just how overwhelmingly vast it really is, and once you understand its scale, a fascinating question appears: what would happen if we tried to cross it? Our solar system sits roughly halfway between the center of the Milky Way and its outer edge, about 25,000 light-years from the galactic core. We orbit quietly around the center of the galaxy without even noticing it. Every second Earth moves through space. Every second the Sun carries us along a gigantic path around the Milky Way, yet despite all that motion we remain trapped inside a tiny neighborhood of a galaxy so large that our minds struggle to visualize it. On a clear night, you may see a few thousand stars scattered above you. That already feels impressive. The sky appears packed with distant suns shining in every direction, yet those visible stars represent only a tiny fraction of what actually exists inside the Milky Way. The overwhelming majority remain invisible to the naked eye, hidden by distance, dust, or their own faint brightness. Red dwarfs alone outnumber stars like our Sun by enormous margins, yet most are far too dim to spot without powerful instruments. Astronomers estimate that the Milky Way contains somewhere between 100 billion and 400 billion stars. The true number may be even more surprising because many discoveries continue to reshape our understanding of the galaxy. Around countless stars orbit planets. Some systems contain rocky worlds, others host giant gas planets larger than Jupiter. Some may possess oceans, atmospheres, and conditions that resemble Earth. Scientists believe there could be hundreds of billions of planets in our galaxy alone, perhaps even more. The exact figure remains uncertain, but one thing is clear: the Milky Way is crowded beyond imagination. Now consider its size. The diameter of our galaxy is estimated to be somewhere between 100,000 and 200,000 light-years. To appreciate that number, you first need to understand what a light-year actually means. It is not a measure of time, it is a measure of distance. Light travels at nearly 300,000 kilometers every second, fast enough to circle Earth more than 7 times in a single heartbeat. In 1 year, light covers about 9.5 trillion kilometers. That distance is 1 light-year. The Milky Way is not 10 light-years across, it is not 100, it may stretch across as much as 200,000 light-years. Even saying the number feels unreal because human experience offers no comparison. We evolved to judge distances between cities, countries, and continents, not galaxies. We can drive across a nation, we can fly across an ocean, we can travel around the world, but galactic distances belong to an entirely different reality. Imagine shrinking the Milky Way until it became as large as an entire continent. At that scale, our solar system would practically disappear. It would be smaller than a microscopic organism, invisible without magnification. Everything humanity has ever known would be reduced to something so tiny that finding it would be nearly impossible. That is how insignificant our local neighborhood is compared with the galaxy surrounding it. And here is the truly humbling part: the Milky Way itself is not especially unique on the largest cosmic scale. It is merely one galaxy among an estimated 2 trillion galaxies scattered throughout the observable universe, each containing enormous collections of stars, planets, and mysteries of their own. Our galaxy feels limitless only because we live inside it. From the perspective of the universe, it is a single speck among countless others. Understanding this scale changes the way we think about space travel. Crossing a planet is difficult. Crossing a solar system is far harder. Crossing a galaxy enters territory so extreme that even our most advanced technology begins to look primitive. Yet humanity has always been driven by curiosity. Whenever we encounter a frontier, we immediately ask the same question: can we reach it? To explore that possibility, let us begin with the fastest machines our species has ever built. One famous example is Voyager 1, launched in the late 20th century. It continues Racing away from Earth today farther than any other human-made object, it travels at roughly 60,000 kilometers per hour. Astonishing speed by everyday standards. At that velocity, a journey between major cities on opposite sides of the Atlantic would seem almost instantaneous. Then there are more modern spacecraft designed for specialized missions. Some achieved even greater speeds during carefully planned gravitational maneuvers using the pull of planets to accelerate through space. They reached velocities several times higher than Voyager, yet even these accomplishments barely scratch the surface when compared with galactic distances. The current champion among human creations is the Parker Solar Probe, built to study the Sun from incredibly close range. It uses repeated encounters with our star to gain tremendous speed during portions of its mission. It exceeds 700,000 kilometers per hour, making it the fastest object humanity has ever produced. It is a remarkable engineering achievement, representing decades of innovation, scientific knowledge, and international effort. But now comes the shocking reality. Imagine pointing the Parker Solar Probe toward one side of the Milky Way and allowing it to travel continuously without stopping, without slowing down, and without encountering any obstacles. How long would it need to cross the galaxy? The answer is staggering: roughly 300 million years. 300 million years ago, dinosaurs had not yet disappeared from Earth. Entire mountain ranges looked different. Continents occupied other positions. Life itself existed in forms unlike anything seen today. That immense span of time would merely represent a single trip across our galaxy using the fastest technology humanity currently possesses. Suddenly, our greatest spacecraft no longer seems fast. It becomes clear that the Milky Way is operating on scales far beyond anything civilization has ever mastered, and that realization leads directly to an even bigger question: if our technology is inadequate, could future breakthroughs eventually solve the problem, or are there deeper limits written into the fabric of the universe itself? The answer depends on whether the future can overcome engineering challenges or whether nature itself draws an uncrossable line. Human history encourages optimism. Every generation accomplishes things that previous generations considered impossible. A person living centuries ago could never have imagined aircraft orbiting Earth, robots exploring Mars, or telescopes peering billions of light years into deep space. Because of that, many people assume future civilizations may eventually discover technologies that allow travel across the galaxy with ease. There is, however, a crucial distinction between technological limitations and physical laws. Technology can improve indefinitely. Better engines, stronger materials, smarter computers, and more efficient energy systems may all emerge. Over time, physical laws are different. They are not obstacles waiting to be solved. They define the rules of reality itself. One of those rules comes from Einstein's theory of relativity, which tells us that an object with mass cannot be accelerated to the exact speed of light. Reaching that ultimate speed would require infinite energy, and infinite energy does not exist anywhere in the known universe. Yet relativity also reveals something extraordinary. Although light speed cannot be reached, it can be approached. If a spacecraft could travel at 99.9999% of light speed, the experience of that journey would become stranger than most science fiction stories. Time itself would begin behaving differently. According to relativity, the faster an object moves, the slower time passes for it, compared with observers at rest. Imagine astronauts traveling aboard a vessel moving at almost light speed. Clocks inside the ship would tick normally from their perspective. Meals, conversations, and daily routines would feel completely ordinary, but for people remaining on Earth, time would pass much faster. Entire generations could live and die while only a short period elapsed aboard the spacecraft. Another remarkable effect appears at these velocities. Distances in the direction of travel begin to contract for the travelers. The space ahead no longer appears as vast as it does to observers elsewhere. The destination seems closer than it would from Earth's perspective. In a sense, the universe itself compresses along their path. The closer a spacecraft approaches light speed, the more dramatic these effects become. Yet enormous challenges accompany such travel. Energy demands grow to astonishing levels. A tiny speck of interstellar dust striking a vessel moving near light speed could unleash destructive amounts of energy. Radiation becomes increasingly dangerous. The appearance of surrounding starlight changes dramatically, shifting into higher and more energetic wavelengths, protecting both crew and equipment would require technologies beyond anything humanity currently possesses. Still, let us imagine these challenges somehow solved. Consider the Milky Way at its maximum estimated width of roughly 200,000 light-years. Even a beam of light requires 200,000 years to cross that distance. Nothing travels faster, therefore observers outside the spacecraft would still witness a journey lasting approximately 200,000 years. Whether the ship traveled at 99% of light speed or 99.9999%, the difference would be relatively small compared with the scale involved for the crew. However, the story becomes completely different at such extreme velocities. The Lorentz factor grows enormously. Time aboard the spacecraft slows dramatically relative to those travelers. A voyage spanning 200,000 years for outside observers could shrink to only a few centuries. Experienced directly, the crossing of an entire galaxy might feel less like an impossible migration and more like a long multi-generational expedition. From their viewpoint, another strange transformation occurs. The Milky Way itself appears compressed. What seems 200,000 light-years wide from Earth may appear